Alright, so we're moving on to section 2 of chapter 16. We're looking at light and specifically matter. So when light strikes matter, what happens? Let's get it going now. Okay, so transparent. So if something is transparent, if you ever have heard that word, if you think transparent, yes, when something is transparent, that means that the light waves can travel through it. And if you can travel through it, that means you can see through it. So like your glasses, okay, it's a piece of matter, okay, that could theoretically block out the light, but it allows the light waves to go through, okay, usually unimpeded, so they aren't stopped, they just kind of go straight through all the way, so you can still see through. So any type of clear thing, those are known as transparent. Light can travel through it if you can see on the other side. Okay. If it's translucent, okay, that means that light can be transmitted through it, okay, but you can't see through the object. Okay, so this is like if you've ever seen anything that is like privacy glass, okay, or like bathroom glass that are bathroom windows and stuff. Light can come in, but you can't see out or in. Okay, so you can't see it. It basically blurs it. So there's nothing you can really see, but you can still get light coming in. And that means it's translucent. So light can come in, but it's blurred. Last one is opaque. And if it's opaque, that means that all the light that attaches or hits it is absorbed and not, or reflected out, and none goes through it. Okay, so anything that you're looking at, so like right now I'm looking at a computer, I'm looking at a microphone, I'm looking at a table, all this stuff are opaque. I can't see through them. Okay, it's blocking them. When you look at your friend is opaque because you can't see through them. Okay, the light that's hitting them is being absorbed or reflected away. It's not traveling through them. Okay, so that's opaque. So quick overview of transparent, translucent, and opaque. All right, so let's look at colors. So this is a basic prism in which, as white light hits it, because it hits it at an angle, it is taking the light waves and it's separating it, because some of it is going to be slowed down, some of it is going to be slowed down more than others, creating the different wavelengths, which we talked about last section. So if it's got a bigger wavelength, it's more red. If it's got the smaller wavelength, it's purple. And so it changes those wavelengths, creating the colors. Okay, white light is every color. Every single color together will get you your white light. Okay. The spectrum is the rainbow, Roy G. Biv. Okay, so red, orange, yellow, green, blue, indigo, violet, purple, whatever. That's your spectrum, and those are the colors that we can see with our eyes. Okay. And like I mentioned earlier, it's the wavelengths. So if you take green light, and you change its wavelength, let's say you squeeze it together, you shorten up its wavelength from green, it's going to turn it purple. If you take it and you stretch out that wavelength, it's going to turn it more to the red color, okay, if you start at green. And so that is the main cause of colors, is that whatever color you're looking at, so like right now I'm looking at something blue, it's because the light that's reflected off of it is reflecting back at a certain wavelength that is in the color of blue. Okay, so your primary colors. So when you think of primary colors, like when you were in school, you were probably like, oh, my primary colors, it's red, and that's blue, and it's yellow. Well, light, those are not the primary colors. Your primary colors for light are red, green, and blue. Okay. So the main difference here is that with light, green is a primary color. Okay. And the reason is because if you take red, blue, and green, and you mix them all together, you will get white. And all other colors can be made from those. Again, talking about light, not in art class where, yes, the primary colors when you're dealing with paint and everything is yellow and all those. But when we're talking about light, it's red, green, blue. Now, if you've ever looked at, let's say, like stage lights, okay, or lights like in gyms that have multicolors, there's only 3 colors. If you look real close at an older TV, I don't know newer ones because I don't, stare super close in the TV, but if you look real close at a pixel, it's 3 colors. It's red, green, blue, because with a mixture of those 3 colors, you can create any color. Your secondary colors are the mixing of 2 primary colors. Yellow is red and green, so no blue. Cyan is green and blue, so no red. And magenta is red and blue with no green, okay? And you can fluctuate how much you want of each, and it's going to get darker or lighter. It's going to, it's going to cover all the other ones. But if you just take yellow light or red light, green light, mix them together, you're going to get yellow, okay? All right, complementary colors. So if you have 2 colors, or complementary colors are when you take 2 different colors, you add them together, and you get back to white. Okay, so if you take the 3 colors, red, green, and blue, okay, if you take any of those, or if you take all 3 of those and combine them, you're going to get white. Okay, now if you took 1 primary color and 1 secondary color, let's say you take cyan, okay, so cyan is green and blue mixed together. So green and blue mixed together get you cyan. What color is missing to get you back to white? That would be red. So if you had cyan and then you added red to it, you would go back to white. And those are complementary colors. So if you look over here on this image, you can see it. There's cyan. Opposite cyan is red. That makes you white. This magenta, opposite is green, get you back to white. Yellow, opposite yellow is blue, get you back to white. Okay. And what's happening is that when we have these wavelengths, okay, and as they're bouncing off everything, the objects are absorbing certain wavelengths and reflecting others. So if you look at something that is green, okay, on this screen you see this green section right here. Okay, the light that is reflecting off of it, if you want to think of it in the real context of the problem, and that light, if you see something that's green, so I guess that example of that because it's just straight green light, but let's say you're looking at something that's green, that object is absorbing basically red and blue light. It's absorbing all the red, all the blue. It's absorbing it all, but it doesn't take the green. And because it doesn't take the green, it reflects the green off back to you in your eye. Your eye and brain take that wavelength and go, oh, this is what it is. Turns it into green for you. Okay. All right, so pigments and dyes, just so we know the difference between them. So a dye are molecules that absorb certain wavelengths. So if I'm looking at this red bag, okay, so I'm looking at a red bag right now. What's happening is that it's been dyed, okay, and those molecules are basically absorbing every single wavelength except for the red ones. And you can think it's going, nope, I don't want the red, but I want everything else. The red comes off of it, and then that's what we see. So we see the colors that are not being absorbed by the objects. So whatever object you're looking at, the color you see is the color that is not being absorbed by that object. Okay, it's not, those wavelengths aren't being accepted by it. Pigment compared to a dye, pigments are usually larger. They're made of organic material. I mean, that's kind of the big difference there. Primary and secondary with these. So looking at pigments exactly, primary pigment colors, they absorb only one color. Okay. Yeah, so your primary pigments will only absorb one color of your red, green, blue. Okay. So a primary pigment that is only absorbing one color means that if, red, green, and blue light hits it, it's only absorbing one of those. It absorbs blue. What color do you see? You see yellow. Okay. You see yellow. So that means that the primary colors for your pigment are the secondary colors of light. Because if you have the three primaries hit it and only one is being absorbed, you're left with two and they get mixed together. Your secondary pigments absorb two of the colors. So if you have a color that absorbs red and green, you're left with just blue. And so the object that you see is blue, and that's your secondary one. Okay. All right, polarized light. So light moves in an infinite number of directions when it's, being shot out, kind of like, if we think of it like a ray or anything, it's moving in all the directions. Okay. It's a wave, so think of like a sine curve, okay, going up and down, up and down, up and down, but it's going to be hitting all the way around. Okay, so it could be going north, south, east, west. It could be going diagonals, and all that stuff. Polarizing light, what you do is that you take, you basically make a lens that only allows light to travel in one direction. So I have light that travels north, south, east, west. Okay. So I have light that travels north, south, east, west. So it's traveling this way, and this way, and this way. So it's traveling in all the directions like this. What a polarized lens does is it basically allows only one direction. So it goes, oh, out of all this light's going in all these directions, I only want it to be going up and down. I do not care about it going any other direction. And so we'll only let in up and down light. So when that happens, it's, you've got shades. But if you have two objects that are, they're allowing up and down, but then you put them perpendicular to each other, it's not going to let any light in, because the first one's allowing only up and down, the second one's only allowing left and right. And if you allow only up and down through, and then it hits one that's only allowing left and right, it's not going to allow any light through, because you basically canceled it out. Okay. And so that's how polarized glasses work, how you can see it one way, but then you twist it and you can't see it the other way when you overlap them. Because there's basically a whole bunch of lines, and that's where the light's allowed through. And if you put them perpendicular to each other, it's not going to allow any light in. Because, again, if it's only allowing north and south in, and then the next one's only allowing east and west, well, you can't have north, south, and east, west. It's either traveling north and south, or it's traveling east and west. Right? All right, that's the end of chapter 16, dealing with light. We'll be moving on to reflection, refraction next.